Good morning, good afternoon, and good evening, and welcome to Oliver's webinar, The Fundamentals of Adhesive Coatings. I'm Jen Goff, Global Director of Product Strategy for Oliver Healthcare Packaging, and I'll be your moderator today. We have just a few brief announcements before we begin. First, this webinar is designed to be interactive. In the bottom right corner of your screen, you have the opportunity to click Chat and Q&A. If you're experiencing any technical issues during the webinar, please use the chat function so we can do our best to assist you. Use the Q&A function to ask questions that relate to the content of the presentation. You can check a box to make sure your question is asked anonymously if you would prefer. And now on to the presentation. Discussing today's topic are Kevin Zacharias, Technical Director for Oliver Healthcare Packaging, and Sarah Weber, student at UW Stout, University of Wisconsin Stout, packaging engineering student. So without further ado, Kevin and Sarah, we are looking forward to this webinar and all of the information you are going to provide for us. Sarah, take it away.
Thanks, Jen, for introducing us. Today, we are incredibly excited to share our knowledge of adhesive coatings with you. As a student myself, I only had limited knowledge on this subject when I started my first internship in the healthcare industry, and I'm sure many entry-level engineers are in the same boat. So let's dive right in with the basics. Kevin, can you define what adhesive coatings are and why they're important to use?
Sure. So because this is a fundamentals webinar, I'm assuming there's quite a few folks on the line that don't have a ton of experience. And so if you haven't noticed, one thing that's prevalently common in our industry is the use of acronyms and also interchangeable terms to mean the same thing. So it can be a little bit confusing. So, hey, why not start out the first slide with throwing an acronym out there? So HSC, you might see that on your specifications or documentation. What HSC stands for is heat seal coating. So that's one reference to these coatings, but you might also see them referred to as adhesives or coatings or coated adhesives, you know, all the above. And even sometimes I'll see the term glue used, and that's really not my favorite, but it is what it is. So what are these things and how are they used and what's the purpose? That's a great fundamental place to start, as you said, Sarah. So generically speaking, and again, this is a fundamentals course, so we're going to keep things pretty high level and we're going to do a lot of simplification. But generically speaking, what these coatings are they're comprised of polymers and typically in the form of EVA, which is ethylene vinyl acetate, and they have waxes, resins, and other fillers that are part of their formulation, and we'll get into some more depth on that later. But they are generally applied to papers, films, and probably most commonly is DuPont Tyvek, and we're going to use a lot of references to DuPont's Tyvek just simply because it's so commonly used. And so what are they for? They're there to allow for a peelable seal. So that makes them obviously a very important part of the sterile barrier system. So the picture on the top of the right is basically a flexible form-filled seal blister with a Tyvek lid that has been peeled off. And you can see on the film or on the forming web, you've got that nice white opaque transfer. And that's giving, per the fourth bullet point, a nice visual assurance of the seal integrity for the clinicians out in the field. And the pictures on the lower right are simply under magnification what some of these coatings might look like. The picture on the lower right is a flood-coated coating, very commonly used in our space. And then on the lower left there is a blue dot coat. So there's just different types of technologies out there. Some are micro dots put on the substrate, some are flood-coated. And the common thing with all of these heat seal coatings, per the bottom bullet point, is that they need heat to make them work. So hopefully that kind of gives you a good foundational description, Sarah.
Yeah, it definitely does, Kevin. Thank you so much. So I'm curious, what type of applications are coatings used on? Do we need them in all sterile barrier packaging applications?
Well, that's a great question. And so again, back to this is a fundamentals course. So I'm assuming that not everybody on the call has worked in all the different applications that are out there. But I think it's just good to kind of set the table with this. So there are primarily three different types of platforms, if you will, and this doesn't cover everything. There's other applications out there, other types of configurations, but generally speaking, these three cover vast majority. So they're broken down into, and what we have here is a picture of the components, and then the equipment on the bottom of the slide is typical heat sealing equipment that might be used to process them. So on the left, pouches, very commonly used, and these are generally pre-made by a converter / supplier like Oliver. And then the MDM, medical device manufacturer, there's another acronym for you, would put the device in and then do the final seal. And these sealing equipment look kind of like, pretty much bench top, like the lower, or, the picture on the bottom there. And then lids and trays. So think about a thermoform tray with some type of a lid, and heat seal coating would be applied to that lid. And that picture in the middle on the bottom is a typical kind of shuttle sealer that might use to seal a lid to a thermoform tray. And then, hey, there's another acronym, TFFS, and that's another common application. TFFS stands for thermoform fill seal. And Oliver, other suppliers would be typically supplying materials in roll stock form. That's a picture of some coated Tyvek. And then there would be another formable film on the bottom, and the machine there on the lower right is kind of a typical, what a typical thermal form fill seal machine would look like. So those are the three general applications. And to answer your final question, Sarah, do all applications need to have a heat seal coating in play? Not necessarily, and especially with pouches, there's a lot of pouches that do not have a heat seal coating as part of the equation, but we can get into that a little bit later as well.
Thanks, Kevin. It seems that I'll have to probably make a cheat sheet with all these acronyms you're throwing at me lately. So I heard in the last slide that you mentioned that adhesive coated substrates need heat to make them work. Can we circle back to that and have you explain what the heat sealing process is with respect to coatings?
Yeah, absolutely. And I think you made a great point. Having a cheat sheet with all the acronyms and terms is actually great advice for anybody new, or even 5 years in or 10 years in. It's always a great reference tool to have. A lot of us have that, so that's a great point. But yes, let's move into the heat sealing process. And so, like the webinar has stated, it's fundamentals of coating. So this is also very fundamental heat sealing, or heat sealing basics. So, but again, it's as a packaging engineer, all of you that are working in heat sealing processes, be curious about how this works. You'll be able to identify risk in this process, but let's just break it down very generally. So you have three primary inputs into a heat sealing process. So temperature, which is pretty obvious. That's the temperature needed to activate the coatings and get the sealants to work. Dwell time, so that's the amount of time that your heat source is in contact. And then pressure is the amount of force applied to the materials to get them to marry up or contact each other. So if you're doing a design of experiment, as the slide indicates, temperature is going to be is typically, and we're speaking generally, is typically going to be your most influential input. So remember that when you're doing a design of experiment. And pressure is typically your least influential input, but you also have to be careful with pressure, and because it can cause some risks that we'll talk about later. And then the diagram in the middle bottom there is just, it's not meant to be, those numbers aren't reflective of every heat sealing process and material combination, but just gives you, as an engineer, it gives you kind of a concept of what's going on. So if you have a heated platen that's part of your heat sealing process, you're essentially getting that heat to soak through the materials. We're going to keep using Tyvek from DuPont as an example. So you're getting it to soak through the Tyvek, and then soak into the adhesive that's coated on the Tyvek, and get that adhesive to activate, and ultimately enough temperature and dwell time to get the adhesive to activate and bond to the sealing substrate, like a film that you're trying to get it to bond with.
Absolutely. That's some great foundational information about heat sealing here. I know that it's important for engineers to understand the parameters around heat sealing, right? Can we dive a little bit deeper into some potential risks that could be associated with under sealing or over sealing if you have the wrong parameters?
Yeah, absolutely. Absolutely. So I recommend with engineers, it's nice to kind of play around and see what happens, but We have a couple of slides to talk about the term undersealing, which we use commonly. And so it's pretty common for us to receive input from a customer that maybe they're using a coated Tyvek lid for the first time, and the pictures on the right might be an output from that sealing process. And so you can see it's kind of like we talked about the adhesive on the tray flange. Well, in this case, there's a lot of gaps and voids and spottiness. And so it's obviously not a good looking seal. A clinician will look at that and be concerned that it's, there's not a sterile barrier anymore. So common for us to get a call and say, hey, Oliver, what's wrong with your coating? It's not working right. But this is a scenario where in an undersealing world, we're basically, just as the term implies, we're underdoing it, right? So we're going to look at a couple different outputs. So visual, that's telling you that, hey, there's not enough something during the heat sealing process to get the coating to fully activate and bond to that tray. And so that's visual. And then the chart on the lower left, if you're not familiar, if you're all not familiar with a seal curve, I mean, this is a very common tool to look at outputs from the sealing process in terms of seal strength. So the y-axis is seal strength in pounds per inch, and the x-axis is the temperature of your sealing process. This one happens to be in degrees Fahrenheit, but kind of going from 200 degrees Fahrenheit up to 300. And then what is the output in seal strength at those temperatures? And for this, you can just assume that dwell time and pressure are consistent throughout the whole process. So the output here, obviously, is the visual look of the seal is not good. And then the seal strength that's being output in that little red dotted circle down there is telling us that the seal strength is like around a half a pound, and it's not optimized. So you kind of have two outputs telling you that you're not getting enough temperature, pressure, and dwell.
That's very interesting, Kevin. What I see on this slide here is that poor adhesive transfer may not directly correlate to an issue with the coating, but it could be a problem with your heat sealing process. Can you give us an example of when you may see good adhesive transfer, but maybe it doesn't meet a seal strength requirement? Why is it important for us to understand both of the aspects here?
Yeah, that's a great point. So the advice is, if you go to the next slide, you don't want to necessarily just focus on visual appearance. You want to look at it from multiple angles. So in this particular slide, we have examples on the right of a seal that looks really good, right? I mean, I think, Sarah, you would agree, the lower right, that's another flexible form-fill seal blister, and that the perimeter seal, the transfer of the adhesive looks fantastic. The pictures in the top show that there's no voids, no gaps, no spottiness. So you think, hey, we got an optimized seal. But in some cases, you can have a good visual appearance, but you can still have an output of seal strength that is not optimized. So this is just showing, again, we're looking at a seal curve on the left. Even though the transfer and the visual appearance looks great, your seal strength is still below a pound. It's not hitting the full capability of the coating. So more work needs to be done. You need to look at it from multiple angles, and that's really the primary message.
That's great information. So as engineers walk through their design verification process, I think it's common that there's only a requirement around a minimum seal strength. So can we kind of talk about the other end of the spectrum here with a risk associated with oversealing? What could be the result of having a seal strength that could potentially be too high?
Yeah, it's a great point. And this slide is going to speak to that. And I would say, from my personal experience, I think folks are more likely to go to this end of the spectrum versus the other end of undersealing, because, I don't know, maybe it's just human nature that more is better. So it's common for our customer base, and even earlier in my career, I often took this approach where I would want to maximize temperature, pressure, dwell, and get what I thought was a really robust seal. So this is as you stated, this is the other end of the spectrum. And so if you go too high in temperature, pressure, and dwell, you can get some degradation of the materials. So in this case, we're showing Tyvek, and some of the telltale signs are, the darker appearance of the material in the seal. So the Tyvek is essentially starting to melt and turn transparent, which makes it look dark. So that's an indication that perhaps you're oversealing. Other indications are that the seal flange can kind of like start to curl and warp. So if you've got a thermoform tray, the tray material starts to warp and curl, or the pouch, etc. And that's another potential sign that you've got too much going on with your sealing process and you need to dial it back a bit. And then the lower right, some things, materials start to degrade, as I mentioned, and like this case, Tyvek can start to delaminate or tear or shred. And so what that means is that you're reaching the maximum capabilities of the material. So to answer your question, Sarah, you may really, from the top end, you may want to look at the material starts to break down, like I said, and that's really where you don't want to be. And maybe it's less about the seal strength output, and more about what are the materials doing. But you can't forget about seal strength as well, because at the end of the day, the end user experience is important, and being able to get into that sterile barrier is important. But the seal curve on the left is just showing that, hey, you've gone above where you're consistently getting seal strength output, and the materials are showing it.
Yeah, so now that we're kind of getting into a conversation about the end user and aseptic presentation, which is a very hot topic in our industry right now, I'm always curious to learn about how materials can be better than others in certain applications. Can we discuss the difference between using a coated or uncoated material, and when it could be beneficial to use one over the other?
Yeah, sure. It's another really good point. So let's look at this slide. And I think I said earlier when the question was asked, are all sterile barrier systems, do they need to have a heat seal coating? And the answer was no. And so this is an example of pouches. So very common for many decades for there to be uncoated Tyvek pouches in our industry. Oliver makes thousands of these every week in our various sites. So they work great in many applications. Oliver also makes coated Tyvek pouches. And so the differentiator, it can depend on the application, Sarah. So, one thing that can kind of dictate use of an uncoated Tyvek versus coated Tyvek is, we see, and we make a lot of pouches for catheter applications, and catheter pouches are commonly very long, very narrow, sometimes 40, 50, 60, even 70 inches long. And in those applications, there can be quite a bit of sensitivity to materials tearing or fiber creation. So it is common for us to use a coated Tyvek pouch. So in the lower left, you can see what that might look like under magnification when you peel the Tyvek up from the film, and the coating is providing some risk mitigation for material tearing and fiber pickoff and so forth. And the picture on the top of an uncoated Tyvek pouch, think about peeling down a 70-inch pouch. It affords more potential for risk of material breaking down or tearing. So it's like an insurance policy, if you will, that for a long, narrow pouch, that coating can really help mitigate any risk of Tyvek tearing or shredding or other materials as well.
Yeah, that's great, Kevin. So now we've discussed the heat sealing process and the risks associated with under and over sealing, as well as the trade-offs between coated and uncoated materials. So what are the factors that we should think of when we're trying to optimize our heat sealing process? Is there a golden ticket?
Well, hopefully there's a golden ticket. And hopefully you've got a sealing process and materials that are capable of having optimized window. As we know in our space, and per ISO 11607, I mean, you need to have a sealing process that gives you a window to work within. And so most of us are going to know that you have to have that low and high setting in your heat sealing process. And at both settings and in between, you can produce product that meets specification. So this slide is basically showing, hey, you've got a good looking integral seal, like we've been talking about, the pictures on the right show that, and then a seal curve where you've got a pretty good consistent output of seal strength. And so therefore you've got, a temperature window of, I'll just pick some numbers off of this chart on the lower axis, but 240 to 260 degrees. You have a nice temperature window, so you can make pouches at a low temperature, low dwell, and low pressure, as well as high. And that's really, there's other things to look at besides just seal strength and visual appearance, but that's generally where you want to be. And that's like the golden ticket, Sarah, as you mentioned, to get to a point where you've got a nice reproducible window to work in your process, in your operations.
Thanks, Kevin. So now we are going to transition into our first poll question. The poll question is true or false. The question reads, adhesive coatings are necessary on all flexible medical device packaging. I'll give you a few moments to answer and then we'll discuss. All right, so the majority of our audience said that the answer was false, and that is correct. Kevin, do you have any thoughts on this one last time?
Yeah, I mean, as we've been talking about, adhesive coatings are very advantageous in a lot of the applications we've been talking about, but they're certainly, they're not required in every application. And I mentioned that, especially in the world of pre-made pouches, with the different film technologies that are available, you don't necessarily have to have a coated Tyvek in play or a coated paper or what have you. There's sealant technologies that can be used or applied within films and so on. So it's not, the answer, is false. You don't have to have a coating in every application, but it can be advantageous in quite a few. Okay, great. So now I want to dive a little bit deeper into what coatings are actually made of. In ISO 11607 Part 1, it mentions that all materials need to be documented and known. In addition, I just think a lot of engineers are in the same boat with me when I say we just are genuinely curious about what our materials are comprised of. Can you walk us through the ingredients of coatings and how they're formulated? Yeah, definitely. And yeah, thanks for, I agree with you. It's really good to be curious and at a high level, maybe some of this information may not seem useful, but the more you can build your foundation of knowledge of the materials that you're working with, the stronger you'll be when it comes to, mitigating risk or troubleshooting. So this slide is going to speak to formulation and what coatings are comprised of. And disclaimer here is that I'm not a formulator. Oliver has a team of scientists that do the formulation work. So we as a supplier are formulating our own adhesive. So it's more the folks with polymer science background, PhDs, chemists, chemical engineers that are doing this work. And so they're dedicated to understanding these materials. And when they're formulating these coatings, and Oliver, I'll just throw it, I think last I checked, we have over 40 different heat seal coating formulations in our portfolio. So there's quite a few and they're all different, but our formulators that are scientists working on these they're working in theories of adhesion and cohesion. So that's a good foundational thing to understand. Adhesion, just as it sounds, when we develop these coatings, we want to make sure they adhere to whatever it is we're applying them to. And we also want to make sure that they adhere to whatever it is we're trying to seal the coated substrate to. So think about a film, if you will. And then also they are working within theories of cohesion. That's a little bit different and maybe harder to grasp. So we're going to cover that a couple slides later, but that's going to be very important. And as we mentioned earlier, the primary ingredients that we're working with that impact these coatings are polymers and generally EVA, ethylene vinyl acetate, as I spoke about earlier, waxes, resins, and fillers. So just from again, that foundational knowledge, what these ingredients look like when Oliver receives them in. I mean, you can see sometimes they're coming in pellet form or beaded, powders. On the far left, that's basically a water-based emulsion of EVA. So it's kind of like a liquid, milky looking materials. So we're blending all these ingredients at very specific ratios to get different outputs of performance, and we'll talk more about that in a minute.
So once these coatings are formulated, I'm curious about the process of actually applying them to the substrate. Can we talk about that a little bit?
Yep, and that's a really good thing to understand. So we have an animation that shows one of the very commonly used coating processes. This particular animation or technology shows an air knife coating. So we'll get into that, but basically we're taking wide web substrates. Going to keep using Tyvek, so that's maybe a 55-inch roll of Tyvek. We're running it through a series of rollers, and then essentially we're going to be flood coating it with one of our coatings at an applicator station. This is kind of demonstrating that. So flood coated at room. This is all done at ambient temperature. And then this is an air knife that's going to be metering off the excess adhesive into a blow-off pan, and then that coated substrate is going to go up through a series of rollers. It's going to have some coat weight check, and then it's going to go into a series of drying ovens to flash off. In this case, it's a water emulsion, so it's going to flash off that water. So you've just got a solid, nice breathable coating on the substrate. And then it's wound off into master rolls. And those master rolls of coated substrate are going to be routed through other converting processes at Oliver, like converted into pouches, or they're going to be printed and die cut into lids, or printed and slid into rolls for form fill seal applications. So that's kind of like generically what a typical coating process looks like, whether at Oliver or at one of the other suppliers out there of heat seal coatings.
Yeah, that was a great visual representation of the process here, Kevin. I heard you mention that after the flood coating process on the substrate, the excess coating is then swept off. Is that leftover formulation then recycled and reused back into the process to avoid unnecessary waste?
Yeah, definitely. So it's recirculated through the system. It's a really good observation. So yeah, it's not just wasted. It is recirculated in the process to minimize the amount of waste. Correct.
That's great to hear. So once a coating is formulated and then it's applied to the substrate and eventually sealed, how does it actually work and add value to our package? Maybe we can go back to the theory of cohesion on this.
Yeah, definitely. So cohesion. So we talked about adhesion and we talked about cohesion. So our formulators are, they're working in this theory. So a cohesive peel is going to look like, let's just look at the lower right for a second. That little diagram is kind of a basic diagram of a tray that has let's say a Tyvek lid that's coated. So when you peel off the lid, the coated lid, and what you've got left is there's actually that coating is splitting cohesively. So some of it's staying on the Tyvek, and then some of it's staying on the tray flange, which gives you that nice visual recognition of the seal. And then this video that's running on the left under magnification is essentially a side view of coated Tyvek that's being peeled off of a PETG tray flange. So you can kind of see under magnification that coating is splitting, and some of it's staying on the Tyvek lid and some of it's staying on the PETG tray flange. And it's kind of, I love this video because it shows it's very tangible and you can kind of see that. So that's what cohesion is all about, or cohesive working coating. That's what it's all about. So back to the formulation aspect, our formulators build into the coating cohesive strength, and it's got to be appropriate so that it works and some of it, and it splits and it doesn't completely pull off of the substrate. So think about the output of seal strength or peel strength that we've been talking about. We as formulators control that peel strength by controlling the cohesive strength of the adhesive. So kind of like the inner strength of that coating, how strong that is dictates the output of seal strength, whether it's 1 pound or 2 pounds, etc. So this is a really important thing to understand when you're working with coatings and as an engineer at a medical device manufacturer. Hopefully that kind of answers that for you.
Yeah, of course. Just to jump in here, I think it's important to note that not all coatings are made equal, and it seems like there's a lot of different coatings to choose from. Like you said, that Oliver has over 40 different formulations. And so when you formulate these coatings, it may result in different characteristics and properties in addition to just this cohesive strength that we talked about here. Can you dive into how formulation changes can affect different performance outcomes in our package?
Yes, and let's use an example. So as you stated, yeah, there are a lot, Oliver alone, 40 formulations. There's other ones out there in industry. So they're not all the same. They're not all formulated the same. And so I'm not going to get into the details of this. This is as they say, an eye chart, if you will, but some of the characteristics that our formulators are working towards are listed in the left side. And then basically what this table is saying is that we're working with balancing the ratios of these different ingredients to give us different outcomes and characteristics of the coating itself. So this is not all inclusive. It's very simplified, even though it looks complicated. It's simplified even further than reality. And so some of the characteristics we're looking at are adhesive strength, and we talked about that a minute ago. Cohesive strength, which we just talked about, and that's driving the end user experience with peel strength. Adhesive transfer, so we can formulate to make the appearance of the seal look more opaque and white versus less, so that's an important characteristic. Hot tack is an important characteristic, especially in thermal form fill seal applications, and that's really kind of talking about how quickly does that coating set up and come to strength after it's been sealed, and that's critical. Cold shock would be relating to how does this coating perform in a cold temperature, whether it's dropped, so think about that shock, and not all coatings are equal in that regard. Anti-block is another characteristic, and that's kind of thinking about how tacky the coating is, if it's too tacky. If you have a roll stock rolled up with a coating on it and it's so tacky that you can't peel apart, it starts to unwind and it's sticking together, sticking to the backside of the substrate. That's kind of, so we have to formulate so it's not so tacky that it sticks together and without making it problematic to use. So the arrows are basically saying, hey, go up and down in your different categories of ingredients and balance them to get different characteristics in regard to some of the things on the left.
Yeah, so like I said previously, many engineers think about having the need to increase their seal strength to meet certain requirements in their design verification. But I see on this slide that some formulation changes in coatings could result in a slightly lower adhesive or cohesive strength. Do you have an example of where an engineer might need to just lower their seal strength or increase it instead of increase it? Could a coating formulation potentially be the solution to that problem?
Yep, definitely. And so generically speaking, yeah, you can modify the ratios of the ingredients to get changes in seal strength. So one situation kind of stuck in my mind as we prepared for this webinar, and it was true story, where we had a customer that was kind of had a unique application where they were focused on an end user market of arthritic folks. So it wasn't a typical application, in hospitals. So it was a specific device that was going to be used for home use in arthritic patients. So the primary seal strength, the coatings of the seal strength of the coatings in most of the portfolio were simply too high. So they came to us and said, hey, can we reduce that? And the caveat here is that there has to be significant enough volumes for Oliver to kind of go down the path of reformulation, because we just saw what a coating process looks like, and you can imagine that for small volumes we couldn't really do that. But in this situation, we were able to do it. And if we go to the next slide, we can talk about how that works. And I'm going to have to keep saying this this is really simplified. Our formulators, it's a more complex than this, so they'd get mad at me if I oversimplify. But this is kind of how the approach would look. So taking an existing coating that maybe was giving a 2 pound per inch seal strength was too strong, too difficult for the end user to open up the package. So back to that, the tables that we looked at a minute ago, and cohesive strength, and remembering that cohesive strength is like that internal strength of the coating, and it dictates the end user, seal strength. You could do this with the formula. So you could increase your waxes and resins and fillers and decrease the polymer, which again is typically going to be the EVA. And that's basically the roadmap to decreasing the cohesive strength, which in turn decreases the seal strength. So the seal curve on the right was kind of the output of what the seal strength was. So the red line was of the existing coating, and it was tracking around 2 pounds per inch. Again, it was too strong for this application. So after rebalancing the formulas, we didn't have to introduce any new ingredients. We just had to do a rebalance. It dropped the seal strength to 1.5, 1.6 pounds, and that's exactly where it needed to be. So that kind of just gives like a real basic example of how formulation works and how different characteristics, and in this case, seal strength, can be adjusted with ratio rebalances.
Yeah, that was an awesome example for us, Kevin. I really appreciate it. So now we're going to transition into our second poll question of the webinar. This again is a true or false question. So the question reads as follows. If your coating is giving you a 1.5 pound per inch of seal strength at room temperature, the seal strength is also 1.5 pounds per inch in the EO chamber. True or false? Okay, so the results are in here. So the majority of people said that it was false, and there was a few people that said that it was true. Regardless of the answer here, Kevin, which the answer is false, it is different in the EO chamber. Why does it matter? Why is it important for us to understand how our coatings react in an ethylene oxide sterilization chamber?
Yeah, I think this is one of my favorite poll questions. So I think it's all about risk. So if you think about risk, and we're all focused on that, it's a good, and I keep saying foundational, but it's a good foundational thing to understand that during ethylene oxide sterilization, we know that the temperature is increased. Generally, the cycles I see are tracking at like 132 degrees Fahrenheit or 55 degrees Celsius. We know there's high humidity. We know there's vacuum as you're pulling the gas in and out of the package. So really important, if you're not listening to anything else, just listen to this. It's really important to know that the seals and the heat seal coatings are used are going to be weaker at that elevated temperature. It's going to vary by material. We're going to talk about that. And not all coatings are the same, but just understand there's a risk component that at elevated temperature, the heat seal coatings are going to be weaker. And an example of one of the risk scenarios, which we'll talk about in the next slide, is if you heard the term sterilizer creep or seal creep, the picture on the right bottom or they're both actually showing kind of like the seal is starting to give way, and that's a result of some type of stress on the seal at elevated temperature.
Yeah, so this is a very interesting added risk into our equation for our packaging design, Kevin. Do you have an example of a seal creep that caused a package failure? And could we potentially run through the root cause analysis of that failure?
Yeah, definitely. So if we move to the next slide, some of the things that are common causes of sterilizer creep are the picture in the upper left is basically a device that was too large for the package. So in this case, the device was sitting slightly above the plane of the seal, just a few millimeters. So at room temperature, hey, it was fine. The seals looked great. and everything passed, but think about the device pushing on the lid just slightly, and then you put it into an EO chamber where we just talked about the risk of weakened seals due to high temperature, and you started to get some opening or seal creep. So those little arrows are pointing to kind of the scalloped areas where the seal is starting to give way. In this case, it eventually, this picture shows that it didn't creep all the way through the width of the seal, but eventually there were other samples that did. So between the stress on the seal, and then we just talked about the pressure going in and out of the package, that can be possible causes. Porosity can also be an input or a potential cause. So the breathability of your substrate. In the lower left, you can envision that's kind of like a side angle of a thermoform tray with a Tyvek lid or breathable lid. And so if you have reduced porosity and you're pulling vacuum in and out of that package, you can see that the potential for the lid to pillow, and the red arrows are pointing to, the potential for stress on that seal as the pressure differentials are bumping back and forth. So just be careful about porosity of substrates you're using, and also be careful with blocking off the porosity with labels and things like that. So those are all things to watch out for and can be potential risk. And then the picture on the right is just showing a dye penetration test. That's a great way to check integrity of seals.
Yeah, that's great, Kevin. Are there any formulation changes that can be used to potentially combat this seal creep?
Yeah, I think if we go to the next slide, the messaging here is that, we've been talking about there's lots of different coatings out there. They're not all exactly the same. They have different formulas and different characteristics. So with respect to sterilizer creep, one thing to look at is how strong are the coatings at elevated temperature, because we talked about how they get weaker, but some of them get weaker than others. And so the bar chart here is just showing a test that we do to rank materials. And so what we've got here is 6 different types of coatings. And what we do is we create a 1-inch wide seal coupon, and we affix a 200-gram weight to one of the tails of the coupon and put it in an environmental chamber at 55 degrees Celsius to kind of simulate EO. And we just see what happens. So higher is better in this one. So adhesive B and D, it's a 120-minute test. So B and D survived for the entire 120 minutes without any degradation of that seal or release of the coating. Whereas adhesive A, for example, at the 50-minute time mark came apart, or the seal basically opened up. So it's just a way to rank. It's not saying that adhesive A or C are not going to work, or they're high risk adhesives. It's just saying, back to the point, they're not all the same. So you also have to be concerned about porosity, which we just talked about. But really, just as an engineer, it's good to be mindful of the coatings and how they perform at elevated temperature. And they're not all the same. Comes down to the choice of polymers that are being used and the levels of waxes and resins, and that can help to dictate the strength at elevated temperature. But it's kind of, the bar chart's kind of difficult. So if you go to the next slide, we take a video of this test just because it's just more helpful. And so you can see the weight is attached to the seal coupon. If we run this video, it's an elapsed time video. So over the course of 2 hours, you have 3 different coatings on the left, or one set of 3 on the left and one set of 3 on the right. And so the coating on the right is essentially peeling apart during this test at some point within the 120 minutes. Whereas the coating on the left, you can see there's no release. So it's basically saying at 55 degrees Celsius, the coating on the left is maintaining strength better than the coating on the right. And again, not saying that the coating on the right is going to be problematic in all applications. It's just kind of highlighting that there are differences. And so the way I look at it is, all else being equal, why not have the insurance policy of a coating that's got very robust capabilities at high temperature or elevated temperature?
Yeah, thank you, Kevin. I really like that visual representation of the creep test. It really puts things into perspective, especially the importance of trying to pick the right coating for your application. So now before we wrap up, I wanted to summarize the topics that we covered today. First, we covered formulations of coatings. What's important to know here is that there are a plethora of different coatings that provide us with different properties and characteristics for our sterile barrier packaging. It's important to be aware of your design inputs and the application of your product so you can have an open conversation with your supplier about having the right coating to use. Next, we discussed the process. Not only did we discuss the process of formulating and applying the coating to the material, but we also heavily discussed the heat sealing process. Like Kevin said, we need to use heat to make the coatings work. Optimizing our sealing parameters will provide us with a nice, clean, peelable seal for our package, and coatings are a key factor in providing that stability in this area. Next, we talked about performance. Again, coatings provide us with a stable and uniform peel strength. It gives us, the end user, the adhesive transfer and effect to visually inspect the integrity of the seal after it's opened. And it will also fight against other risks such as EO seal creep that we just discussed. Lastly, we discussed the types of applications our coatings are used for. Just to reiterate, coatings are commonly used on pre-made pouches, lids for thermoformed rigid trays, and roll stock for forms fill seal applications to, again, stabilize seal strength, provide a uniform peelable seal, and give us an adhesive transfer effect. So Kevin, are there any last minute considerations that we should be aware of?
Yeah, I mean, as we've been talking about, this was a fundamentals webinar, so we didn't get into a lot of depth and we didn't obviously cover all the bases. A few other things that you all need to consider when you're choosing your sterile barrier system materials or coatings. You need to understand biocompatibility. So for Oliver, that's typically going to be, proving cytotoxicity, that it's non-cytotoxic. So most suppliers are going to be able to supply you with that type of information. It's good to get an understanding of aging and compatibility with sterilization modes that you're using. So the graph in the middle on the right there is basically just showing, work with your suppliers to get a basic understanding of sterilization compatibility, and over time, that they're not going to degrade. So this is just a simple seal curve, or not a seal curve, but kind of the output of seal strength out to 10 years in post sterilization. So that's always good to have. Usability, we talked about that a little bit. Peeling down, aseptic presentation, as Sarah, as you mentioned, a hot topic in our industry right now. And then the video that's playing on the left is, I've spent a lot of my career doing simulated transportation testing. So I know that that's a risk point, and as an engineer, I feel like you're crossing your fingers hoping that your simulated transportation study passes without any failures. So we've done these little exercises where we create a window in a shipper carton and kind of show what happens on a vibration table. And that was basically showing that inside your shipper, how you pack out your sterile barrier system inside of a shipper can have an impact. So too much headspace can allow for too much movement, and all the thousands of iterations, as we're seeing in this video, could lead to punctures and abrasion problems and so forth, flex cracking within your package. So all things to be mindful of. Again, not all coatings are going to perform exactly the same in a shock or vibration study. So those are just some of the other there's other things too, Sarah, but that's more or less some additional things to consider when you're choosing materials and designs.
Thanks, Kevin. So before we jump into our Q&A portion, there are a few key takeaways that I hope are going to resonate with our audience. Number one is to focus on product safety. Coatings, again, ensure seal integrity through adhesive transfer. At the end of the day, product safety should be at the forefront of our minds throughout the entire development process of our sterile barrier packaging. And understanding coatings and how they work is a key component to understanding and focusing on product safety. Next, it's important to know the challenges that can be solved with adhesive coatings. We discussed them today, such as increasing or decreasing our seal strength, fighting against seal creep, or providing our end users with a uniform peelable seal. Again, it's really important to know the challenges and be able to talk with your supplier about what you need out of your design inputs and your application. Next, we talked heavily about optimizing our seal window. Whether it's under sealing or over sealing or finding that perfect medium, we need to be aware of how coatings fit into this equation to help us determine the optimal sealing parameter window for our packages. And lastly, there are many coatings that exist out there, and honestly, navigating this process can be difficult as an entry-level engineer. So my advice to you is to lean on your suppliers and your subject matter experts, such as Kevin, and just have an open conversation with them. Today was a very organic and typical dialogue that you could see between a customer and a supplier. And having those types of conversations are one of the easiest ways that entry-level engineers or new people to this industry can really learn a lot of knowledge. So that's my key takeaway. I hope that those resonate with you. We're going to take it back over to Jen to kick off our Q&A portion.
Thank you, Sarah, and thank you, Kevin. Fantastic presentation. Really appreciated the content and education that was included. So we are going to move on to our Q&A portion of the webinar. And as a reminder, please use the Q&A function for this and not the chat box. We've had a lot of really great questions come in throughout the presentation. So I'm going to try my best to get to all of them, but with how many we have, the chances are a little low, but we will try. So I will start with this first question for you, Kevin, and this is with regard to the coating process. The question is, what are the limitations of the drying stage after applying the coating on the substrate? I don't know if we may need some additional context, but if you know what that means, Kevin, I would welcome an answer.
Yeah, I don't really know exactly what the question is driving at. From a limitation standpoint, well, I guess I could answer it like the limitations in temperature are going to be driven by the materials that are being dried. So I'm going to keep using DuPont Tyvek as an example. So if we're running coated Tyvek through our drying operation, obviously, Tyvek is high density polyethylene. So you have to stay away from the melt points of Tyvek. So you're going to have to keep your temperatures in check, or otherwise the Tyvek is going to start to pucker or shrink up. So that's kind of like the limitations are typically going to be driven by the materials that are coated, I think is a probably quick answer.
Thank you. We got a few questions around the porosity of Tyvek and putting a flood-coated adhesive coating onto Tyvek and how it impacts EO sterilization and breathability. Can you speak to that as well?
Yeah, sure. So the animation we showed was, you can imagine that we're flood coating the surface. So in that particular application, that technology, you're counting on the drying process more or less to create cracks and crevices in the coating to allow for breathability. So, I don't have the DuPont literature in front of me, but let's just say generically that Tyvek is around 22 seconds Gurley porosity. So adding the coating might raise your might close off the sheet to the point where it's instead of 22 seconds, it's 45 or 50 seconds. So there's a lot of controls in place in any coating process to manage that, and a lot of checks in place. So that's going to be more or less how it works. There's other aspects of the formulation process that can dictate porosity at the end of the day, but that's a real high level look at. So it's controlled by drying the coating. And then if you're looking at a dot coat technology, that's more driven by the open areas between the dots of coating. And so that's going to be dictated that way. So again, high level answer, but hopefully that kind of resonates with folks.
Thanks, Kevin. This one has more to do with the heat sealing portion of the presentation. The question is, how about instances of a seal meeting seal strength requirements? However, the visual is still seeing gaps and more under sealing defects. So the question is, if it meets seal strength requirements, but the visual is seeing gaps, do you have a good seal?
That's one where we would say, hey, let's talk about it, because there's so many things that could be in play. So I hate to give a generic answer, but if you feel like your seal strength is optimized, but yet you're still getting a poor appearance, it's possible that something else could be happening. You could have potentially some contamination on your sealing surface. You could have some inconsistencies with your sealing process. But yeah, it's one of those things where we love those types of problems because we can help solve them. But yeah, there's just a lot of different potential root causes for something like that.
Thank you. This is an interesting one. So how would you recommend to test seal creep or failure with a medical paper instead of Tyvek?
Could you seal creep with paper? Is that the question?
Yeah. Yep. Seal creep or failure with medical paper. I'm assuming it's a dye test, right? Or maybe that doesn't work. I don't know.
Yeah, I mean, that's another one. We can help you through the test methods and standards, but there's different ways to do that with porous substrates versus non-porous. So I've seen plenty of people using the dye penetration test with paper. It can be a little trickier with the absorption and wicking that can happen with paper. I've also seen people use the bubble leak test, but certainly medical papers are used and have been used prevalently for sterile barrier systems for many decades. So I think there's ways to check integrity.
Thank you. Another question, are the sealing parameters dependent on the packaging materials themselves?
Typically, yes, that's a big influencer. So yeah, again, using Tyvek as an example, and I just talked about melt temperature of HDPE, so that's going to be a factor. If you're marrying together two films that are comprised of polyester, and polyester is going to have a higher melt points, it's not going to have as much problem with temperature. So depending on the materials you're using, you can go different directions in temperature. Same with paper. Paper's not going to melt. So the materials can drive your heat sealing parameters. Also the thickness of your materials. So that will have an impact as well. So if you're sealing a PET G tray that's 30 mil thick, really thick stuff, versus a PET G tray that's only 10 mil thick, I mean, that's going to change your dynamics with temperature and especially dwell time. So it's kind of like you have to look at it from a bunch of different angles: material, types of material, thickness of materials, whether you're heat sealing process. Some heat sealing processes have heat from both sides, meaning top and bottom, and some just have from one side. So that obviously is going to impact your temperatures and dwell times as well. So it's just a lot of factors can go into it. So you just have to be kind of leery of all those dynamics.
Absolutely. Thank you, Kevin. And thank you again, Sarah. That is all the time we have for questions. We do have a lot more questions in here, and we plan to follow up with you all on these great questions that you asked after the webinar. So as you see on the screen, really quickly, you have a QR code. That is our Pack Talk blog. And I am doing a shameless plug of a recent article that we just published on the Wicked Stability team that is working through Kilmer, who are setting out to show that common packaging combinations and sterilization modalities could be placed on the market with a known and supported minimum shelf life, reducing the need for redundant testing. So really cool article out there. If you haven't heard of that, what's going on there, take a look. But again, I want to thank Kevin and Sarah for your time today, and all of our audience members for tuning in. So thanks again, and everyone have a great day.